going to state the Stokes theorem, and also we are going to recall all those results which are used in the proof of the Stokes theorem. So the statement is, if f vector is any continuously differentiable vector point function and S is a surface bounded by a curve C, then the integral over the curve C of dot product of f vector with dr vector is equal to the surface integral of curl of f vector its dot product with n vector ds, right? Where the unit normal vector n at any point of S is drawn in the sense in which right-handed screw would move when rotated in the sense of description of C. So this is very important to note, the description of C. In what sense it is? This theorem also holds good for if I take the surface, this orange colored one, which is bounded by these two curves C1 and C2. The surface integral of curl of dot product of f vector with n vector ds is equal to the line integral over the curve C1 of dot product of f vector with dr vector plus the line integral over the curve C2 of dot product of f vector with dr vector. The result will follow if we join the curves by any two lines. Suppose from P to Q, this is your first line, and joining this to this, that is the point L to M. And then we apply the theorem to the two surfaces thus obtained. The line integral along this PQ and LM will be taken in the opposite directions and will consequently vanishes on addition, right? So let's recall the important results used in the proof of the Stokes theorem. The first one is, if f vector is f1 I vector plus f2 j vector plus f3 k vector, f vector is having the three components f1, f2, f3, then curl of f vector is written as, writing here I vector, j vector, k vector, and here the partial derivative with respect to x, and the partial derivative with respect to y, and the partial derivative with respect to z, and writing here the components of f vector, that is f1, f2, f3. So how we open this? So this is equal to partial derivative of f3 with respect to y minus partial derivative of f2 with respect to z, and then I vector minus partial derivative of f3 with respect to x minus partial derivative of f1 with respect to z, and here we write j vector, then plus partial derivative of f2 with respect to x minus partial derivative of f1 with respect to y, and writing here k vector. And then is partial derivative of y and z with respect to u and v. So this can be written as, writing here partial derivative of y with respect to u, and then partial derivative of y with respect to v. Similarly for z, partial derivative of z with respect to u and partial derivative of z with respect to v. So opening this determinant, we get partial derivative of y with respect to u, its product with partial derivative of z with respect to v, minus partial derivative of y with respect to v, its product with partial derivative of z with respect to u. Then is, by Green's theorem, we have the double integral over the surface S, partial derivative of q with respect to x minus partial derivative of p with respect to y, dx dy. This is equal to the line integral over the curve C, p dx plus q dy. Then is, if x is a function of u and v both, x is a function of u and v both, then we write dx to be equal to the partial derivative of x with respect to u du plus partial derivative of x with respect to v dv. Right? Okay. And at last, dy dz is written as partial derivative of y and z with respect to u and v, and writing here then du dv. So these are the important results which are used in the proof of Stokes' theorem, and the proof of Stokes' theorem will be available in the next content. Okay, thank you. Stay blessed.